All right, so this is going to be part 2 of our integral test practice. Okay, so we have our problem up on the board here. Prove that the sum from n equals 1 to infinity of n over n squared plus 1 is convergent or divergent. Okay, so the first thing that we should do is use our test for divergence. Okay, we take the limit as n approaches infinity of this n over n squared plus 1. And you can already see here, since we have the higher power on the bottom here, you can even do a L'Hopital once if you'd like to get the limit as t as this is n approaches infinity. You can get a 1 over 2n. Okay, so you can see that this is going to equal 0. All right, that means that the test for divergence is not going to tell us anything. So we need to move on. We can try the integral test. Now, what would be that function that we'd be using? Well, that would be x over x squared plus 1, okay? And we want to use it on the interval 1 to infinity. So we need to see if this function is continuous, positive, and decreasing, okay? So first off, is that going to be continuous from 1 to infinity? Well, this is all positive values, okay? So there's no way that this denominator can become 0, so it is going to be continuous. Now, will it be positive? Well, these are all positive numbers, so yes. And will it be decreasing? Well, you can see here that we have an x squared on the bottom. Okay, so if we start to increase this, you can see that the denominator is going to become bigger at a faster pace than this x will be increasing, which means that we are going to have a decreasing function from 1 to infinity. Okay, so since all that works, now we can actually do our integral, and we're integrating this from 1 to infinity. So we do the limit as t approaches infinity of the integral from 1 to t of x over x squared plus 1 dx. Now, this is just going to be a simple u substitution. All right, so we can do that u equals x squared plus 1, and du would then be 2x dx. But since we don't have a 2, okay, what we can do is just eliminate this 2. We can put it as we can divide by it on the other side. Okay, so we get du over 2 equals x dx. Now, we can do our bounds as well. When x equals 1, you can see that u will equal 1 plus 1, which is 2. And we can also see that when x equals t, well, u is also obviously going to equal t here. Okay, so we got our bounds, and then we also have our substitutions. So let's go ahead and substitute in. We now have the limit as t approaches infinity. The integral from, well, now it's going to be 2 to t of, well, this x goes away, right? That goes away. This x dx, not going to be a thing anymore. Okay, we replaced it with a du over 2, so that means we're going to have a 1/2 out here, and we're going to have a du inside. And, well, this x squared plus 1, that's going to be u. So we're going to get a 1 over u du. All right, and, well, the integral of 1 over u, that's just going to be the natural log absolute value of u. So we can write this as the limit as t approaches infinity of 1/2 natural log absolute value of u evaluated from 2 to t. And we don't need these absolute value signs because these are positive values that we're plugging in, so we'll be all good. Okay, we can do our evaluation, the limit as t approaches infinity of 1/2 the natural log of t minus, I could put parentheses here, the natural log of 2. And you can see here that as t approaches infinity, this is just going to become infinitely large. So this is all going to, I guess you could write an equal sign instead, equals infinity. So this is divergent by the integral test. And there is your nice little sentence that, you should probably end up using. I think most people have to, I think that's how they do that in most classes. I know that's how they did it in my class. You had to actually write out a sentence saying what test you used and what, of course, the outcome was. So, I don't know, maybe that's what you have to do, but there it is if that's what you do have to do. So we have another problem up on the board here. We want to prove that the sum of n equals 1 to infinity of rad n plus 4 over n squared is convergent or divergent, okay? Now, first we need to, of course, do our test for divergence. The limit as n approaches infinity of this series here, we got rad n plus 4 over n squared, and we have the higher power of n on the bottom here. You can tell that this is going to equal 0. All right, now this means the test for divergence will not tell us anything, so we need to move on to the integral test. Now, we can try to figure out this with the function rad x plus 4 over x squared. And let's say that we want this on the interval 1 to infinity. Will this work? Well, is it continuous, positive, and decreasing? That's what we need to find out. Okay, so first off, is it continuous? Well, we're not incorporating 0 at all, so of course it's going to be continuous. Is it going to be positive? Well, we're only dealing with positive values here, and there's nothing negative in this function here. And is it going to be decreasing? Well, this is an x squared here, this is a rad x, so this x squared is just going to get bigger and bigger and bigger, so that's going to make this whole thing smaller, and it's going to be decreasing. All right, so that means that we can actually take our integral from 1 to infinity and put a dx here. Okay, so doing that, we of course need to write our limit notation again. Limit as t approaches infinity, the integral from 1 to t of rad x plus 4 over x squared dx. And you may be wondering, like, how are you actually supposed to do this integral here? Like, this doesn't really look like any of the techniques of integration that we've worked with, but it's actually a lot simpler than you think. You have 2 terms in the numerator and 1 term in the denominator, so you can actually separate this. You can have the limit as t approaches infinity, the integral from 1 to t of rad x over x squared plus 4 over x squared dx. Okay? And then it becomes a lot easier from there. I mean, you just get the limit as t approaches infinity, the integral from 1 to t of, this is now x to the negative 3/2 plus 4x to the negative 2 dx. Okay, we can integrate that fairly easily here. We can write that we get the limit as t approaches infinity of, this is going to become a, well, negative 1/2, right? So we get a x to the negative 1/2. And what's going to come out front? Well, that'll just be this out here flipped, which is negative 2. And when we do the integral of this, we get negative 4x to the negative 1. We need to evaluate that from 1 to t. Okay, so let's do that limit here, or let's do that evaluation so we can take our limit. And then we get negative 2 t to the negative 1/2, which you can just write as negative 2 over rad t. All right, and that's going to be minus a 4 over x, which is just 4 over t. Okay, and that's going to be minus, we plug in 1, so we can even just forget about these x's. We'll get a negative 2 minus 4. Okay, if we make this a plus, then this becomes a plus on the inside here. And you can see that as t approaches infinity, well, this goes to 0, this goes to 0, so we end up with just 6. Okay, and since this integral converges, that means that our series is going to converge. Okay, so by the integral test, this series converges. And that's going to do it for this video.
So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series, the explanation video for the integral test, and the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.